Hello, everyone. How many of you are awake? Good, that's happy. I'll make sure that you stay awake. So my name is Vijay Kumar. Imagine reading a book from the last chapter and going backwards, right? So that's really what you're doing, because this is the first chapter. The way these, because of my travel schedule, I wasn't able to come earlier. And in some sense, you've heard some of the details. What I want to do is not change what I'm going to talk about, but instead just give you an overview. And for those of you who are familiar with it, it'll probably help you put things in context. And those of you who are not familiar with the subject area, you'll probably get this if you didn't get the previous talks. Does that make sense? So what I want to do is really step back and take a look at what Lie theory buys you, how it's related to screw system theory, and how you might think about applications in mechanisms and robotics. So a lot of the material that is here is something that I teach to first-year graduate students. So this is really a tutorial. It's not, I'm not presenting any sort of latest research or research results. So let me first start by giving you a quick outline. So you've heard rigid body transformations up to here. So I'll just quickly review it and let you know where I'm coming from. You've also heard about Lie groups. I want to talk about differential manifolds and why Lie groups are important in the context of differential geometry. Visit some basic concepts in differential geometry, which tangents to curves on a manifold, and tangent spaces, and how that relates to algebra screws, and most importantly, vector fields. So that's not something you heard a lot about, but there are basically, on Lie groups, there are two types of vector fields that are particularly important, left invariant vector fields and right invariant vector fields. So I'll say a little bit about that. In addition to tangents and tangent spaces, there are cotangents and cotangent spaces, and those are naturally linked to wrenches, which you've heard about. And then lastly, I want to talk about invariance issues. And then you've heard a little bit about reciprocity, but wrenches and twists are basically reciprocal, and I want to talk about that, and basically a classification of screw systems, and therefore, and related to that is a classification of Lie algebras. So let's plunge right in. All the material I have has been pulled from these four texts. I include here a picture of Ken Hunt, who is no longer with us, but it was because of him I got pulled into doing kinematics and mechanisms. And this book, although it's quite difficult to read, it contains lots of good stuff. So both Ken Hunt's book and Jack Phillips' book really look at the geometry, and you can sort of read the book even though you might not be interested in the mathematics, the underlying mathematical representations. A lot of the material I'm pulling from Richard Murray, Dejan Lee, and Shankar Shastri's book, which I think is the best textbook on Lie groups and algebras as applied to robotics along with differential geometry. So this book by Mike McCarthy, although it says Introduction to Theoretical Kinematics, actually has a lot of the computational tools that we use. Computational meaning doing calculations, not necessarily numerical computations. So these are the four books that you might consider pulling together if you want to learn material that's relevant to what I'm going to be discussing. So this icon represents when I was a grad student many, many years ago, it was the first difficult task that I sort of got involved in. Understanding the geometry of this, and here's a wire model, a brass frame. And here's a test of how many of you were listening before. So what is this object? Come on. You were clearly sleeping during the last two talks. Huh? It's called a cylindroid. It's a ruled surface, which means you can build it out of wires. And but you look at this, and it looks quite complicated. And I'll tell you where this comes from, although it was mentioned.
We'll have to use a mic.
I am using both. missed the most important part of the talk. I didn't turn it on. It's not turned on. Anyway, is this for the audience or for taping?
Yes. Both. Sorry.
Or can I turn this down?
If you put it lower, your microphone on your
Okay. So anyway, this is a cylindroid and it shows up in screw system theory. I'll talk a little bit about this later. So very quickly, rigid body transformations, Lie groups. You've heard about this ad nauseum. So let me just tell you how another way of looking at it. What do you mean by rigid body displacement? So think of an object, O, collection of points. Obviously, it sits in R3. We're referring to real physical applications. And then you want to think about displacements. So the rigid body displacement is basically a map. And you can think of this collection of points being mapped into that collection of points. So that's a map. So what's a rigid body motion? We'll think of a family of maps parameterized by T. It's a continuous family. And so this is G and this is G of T. So it's parameterized by T. Anytime you have a rigid body displacement, you're obviously taking points P and mapping it to G of P. And you're doing it for lots of points. So for instance, you have a point Q, that goes to G of Q. And because you do this, there's also an induced map on vectors. So if you draw a vector from P to Q, that vector gets mapped from G of P to G of Q. So that's an induced map that we call G star V. So if it's a rigid body displacement, you have this property that you have not only a map, but you also have this induced map. So this action is important. In particular, if you ask the question, what makes G a rigid body displacement, there are basically two things that you want to look at. First is that the distance between these 2 points stays the same. You know that. Lengths are preserved. The second has to do with the induced map. So if you take two vectors, V and W, you look at where they map onto through this induced map. They go to G star V and G star W. Then essentially the cross products are preserved. In other words, if you take the cross product and then map the cross product, or if you take the vectors themselves, you map them and then take the cross product, the answer is the same. Right? So those are the two properties that distinguish this kind of a map. And from that, you can also show that the G star map actually preserves inner products. And so if you have orthogonal vectors, that gets mapped to orthogonal vectors. And all of this really leads to reference triads, and these two properties are essentially what formulate or are the basis of the groups that we study. So if you have a rigid body flying around and you have a reference frame, and you've heard both these constructs, so this is a homogeneous transform, obviously a rotation matrix, translation vector. You might also think of this as a group element going from A to B, and that's a displacement map. So that's just by way of notation. So the Lie group SE3 is basically a collection of all of these elements. Okay. When there's a discussion of Rouleau pairs, and that really has fundamentally to do with these subgroups. So you can show that if you take SE3 and you ask if there are subgroups of SE3, so what does that mean? So remember, a group has this composition property and the closure property. That means if I take any two elements from the group, I multiply them, I'm going to get another element in the same group. So what subgroups exist such that this is true? Well, it turns out there's only these subgroups. Right? So SO3 is just rotations. If you take two rotations and multiply them, you're going to get a rotation. You would not get something other than a rotation. But there are other subgroups that are of interest. So this is SO2, rotations in a plane, SE2, which are rotations in translation in a plane. And then there's some funny ones. The Cartesian product of SO2 and T1, translation one direction, rotation about that axis, which gives rise to the helical pair. And so that's another subgroup. But these are the subgroups. Associated with these subgroups are also subalgebras, and then there's a closure property that's satisfied as well. So these are the subgroups one can study, and there are no new subgroups that are of interest if you're looking at mechanisms in 3 dimensions. So the other thing you might actually wonder is about transformations and displacements, and these two things are used interchangeably. And actually, if you look at Mike McCarthy's book, there's a very nice discussion of how to interpret them. It's the same mathematical construct, but you can use it in a couple of different ways. And it's kind of interesting to go back and look at that. If you understand all the algebra, there's actually physical interpretations that are different. Okay, so let me just stop with my introduction and move on to the first idea, the idea that you might want to think about Lie groups as differentiable manifolds. So you know that rotation matrices, and you've seen all of this before, that SO3 is a Lie group. So what does that mean? It has properties of a differentiable manifold. You know that there are 3 coordinates for SO3, although rotation matrices give you 9 numbers, you can do other angles, or you can do any one of these. But basically, it's a 3-dimensional space. And you also know that SO3 satisfies all these axioms. The ones I'd like to focus on are these axioms. So SO3 is a continuous group, which means that this binary operation of matrix multiplication is a continuous operation. The inverse operation is also a continuous operation. So what does that mean? So let's take a very simple example here. Let's take the rotation about the x-axis through theta, and let's take the rotation about the x-axis through theta plus delta theta, where delta theta is a really small number. And let's take another rotation matrix, which will be constant. So the question I want to ask is, what can you say about the product of R and T, where I'm going to change R from this value to that value? So in other words, R of T is going to change, not because T changes, T is held constant, but R changes. So likewise, I can ask you what happens to R transpose of T, which is the inverse of T. So I'm changing R, I have this knob that I'm dialing, which is delta theta, right? And I want you to think about how these things change. How does the composition operation change, and how does the inverse operation change? So the fundamental idea is that, that these operations are actually continuous. In other words, if I change theta to theta plus delta theta, in the traditional epsilon delta definitions of continuity in calculus for single variable functions, you can also show that these matrix functions of matrices are actually continuous. And you can prove this. You can prove this using linear algebra. You can also prove this using other kinds of coordinates. So that's why we call it a continuous group. And that allows us to do all the group operations and all the differentiation operations. Because it's continuous and the differentiation operation can be done as many times as you want, you have the structure of a smooth manifold. So it's something where there is something that there's a differential structure associated with it, in addition to the smoothness property that's associated with it. So what does a manifold mean? Well, it's essentially a set that looks locally like Rn, but not globally like Rn. So clearly a plane looks like R2, but a sphere locally looks like R2, but is not globally like R2. So technically, looks locally means homeomorphic. And what does that mean? Well, homeomorphism is essentially a map so that the map and its inverse are both continuous. So let me take an example to show you. So here's an example, right? So I've got a function -1 to 1 to R. So this is a pretty easy function to understand, and you know that something funky goes on -1 and 1 when the denominator goes to 0, right? But notice that I'm not including -1 and 1. So what can you say about this function? Is this map, going back to my definition of the homeomorphism, is this function homeomorphic? Is this a homeomorphism? Somebody has got to give me an answer, because there's two answers. 50%.
It's no.
It's not?
No.
Why not?
There's 0 in there, so it goes.
But I'm excluding minus 1 and 1.
We have 0 in there, right?
So wait, zero is fine. I can go back and forth. In fact, if I plot this function, these are the things that I want to avoid. So actually everything is nice and smooth. I can go from here, here, back here.
The inverse one, what exists, right? The inverse.
Why? It's monotonic. There's no problem. Right? So I can go from here, back here, even at 0. But let's look at this one. So this one looks benign, right? Nothing goes up to 0. But now I'm mapping this interval 0 to 2 pi onto the circle, except I'm excluding 2 pi, right? So this is the point 0. I go all the way around here, I come back to 2 pi, right? So there's a one-to-one map between points over here and points over here. But if you look in the neighborhood of P, the map is not continuous, because on one side of P I'm at 0, on the other side I suddenly jump to 360 degrees. So this is not a homeomorphism, right? So the key thing is you want to have smoothness properties, and you want never to be able to, never to get into an argument of whether should I do this or that. In this case, there is no argument, because if I look at that function, I can either be on this side, I can either use this representation or that representation, right? So that's the intuitive understanding behind the homeomorphism. So we want a homeomorphism, which means if you have a manifold like this, I must locally be able to map it onto R2 and then go back again. So this should be one-to-one. It should also be continuous. It should also be smooth. Yes?
In the previous slide, if you go back. If you were to exclude 0, would that be homomorphism?
No. If you were to exclude 0, then you would, this point would not, you would not have that point, right? Oh, if you were to exclude this side, so this is an open interval, yes, it would be a straight line. Then you wouldn't capture, this wouldn't be a circle.
Then would that be homomorphism?
Yes, that would be. Because if you take an open interval here, an open interval here, there's no problem. So again, you're trying to map this onto this and then this onto that, right? So you want to go back and forth. So that's sort of the key concept behind a homeomorphism. So smoothness means I want the f and the f inverse to be continuous, but also I want to be able to differentiate it as many times as necessary. That's the idea of smoothness. So in the multi-dimensional case, all these differentiations have to be partial derivatives. Right? So all partial derivatives of f and f inverse must exist and must be continuous. So here are a couple of examples. So if I look at this map from x to y, and I have x1 and x2 here adding up to give me y1, x1 cubed to give me y2, right? So this is a pretty straightforward computation. The question is, can I go back and forth, right? And can I differentiate this function both ways back and forth? Well, the only problem comes in if you take the inverse of this, which is a cube root, which we know has bad things happening because you can have multiple solutions. But if you restrict the domain of this to something where you don't run into that problem, then it turns out it is a diffeomorphism. But here it's not. Right? So the idea is that if you have a manifold, there might be some places which map onto R2. There are some other places which map onto a different way to R2. And so you might cover this manifold with many of these maps. So the idea is, locally, every point looks like R2. And if you run into issues with 1 over x type singularity or some sort of a coordinate representation issue where there's multiple values, what you want to do is choose another set of coordinates. And you cover the entire manifold with these different sets of coordinates to get the right representation. So each of these is called a coordinate chart, right? So this u comma phi tells you that you're taking this section of the manifold and you're representing it in Rn using the map phi. And of course, there's an inverse to that exists as well. And likewise, this section of the manifold maps onto R2 or Rn with this map C, and you can go back and forth. So the key thing is what happens in this overlap area. And in the overlap area, you have to have some sort of compatibility. Right? You want to make sure that if you have this language phi, this language psi, that there's somebody who can translate phi into psi and back again. So technically what that means is if there's a point here which maps onto this, I should be able to go back here and then back there and then back again to that point and then back again. Right? So that's the notion of compatibility, and the infinity means I should be able to not only do this, have this relationship, but have it be infinitely differentiable if I need it to be. So again, the point x maps to phi x, it also maps to psi x, and I want to be able to go from psi x inverse of psi to x, and then forward phi to that. So the composition of phi and psi inverse should be infinitely differentiable. So if you think of what a manifold is, it's something that locally looks like Rn, but globally I should be able to glue on as many of these charts as necessary, and the collection of charts is called an atlas. Right? So for instance, if you look at S2, or the surface of the Earth, we know that we live in a world that locally looks like R2, but we also know that we cannot cover all of R2, all of S2, sorry, with one coordinate chart. So for instance, we might use latitudes and longitudes, but we know that those suffer at the poles. Right? So you want to think about how to cover the Earth's surface with a collection of charts. And again, think about the compatibility between these charts. Right? So how many different charts do you need to cover the Earth's surface?
Three.
Why 3? Why not just 2?
You need probably a different chart for north and south.
Yeah, so this particular representation is flawed because it fails at the North Pole and the South Pole, but there are other representations, and you should be able to think of it so that you only need 2. You need 2. I mean, you can obviously do it with 10, right? But the minimum number of charts you need is 2. Right? So that's useful to know. This is slightly harder, right? So now let's take SO3. Let's take rotation matrices. We've heard about quaternions. We've heard about exponential coordinates. The fact is that even your best representation is going to have some issues on SO3. One chart will not suffice. How many charts do you need for SO3? I think Euler angles. What's the problem with Euler angles? Like you run into problems when one of the angles becomes 0 or pi, right? So that clearly doesn't work. So how many different types of how many different charts do you need to cover all of SO3? Again, the answer is 2. Right? And if you like Euler angles, you could just take 2 sets of Euler angles and work with those. And the only thing you have to worry about is the area where those 2 representations overlap. You have to make sure that there's a systematic way of going from one set of Euler angles to another set of Euler angles and back again, and that mechanism needs to be differentiable as many times as you want. So that's sort of the key idea, and I'll also try to relate some of the things that you learned about earlier. So if you look at SO3, or for that matter, any finite dimensional Lie group, you're guaranteed that there are 2 types of coordinates that exist. So in an n-dimensional Lie group, there are what are called exponential coordinates of the first kind and exponential coordinates of the second kind. So this is essentially the exponential of a vector, a tangent vector, and we'll talk about that. And this is essentially the product of exponentials that you heard about earlier. So Euler angles are essentially something like this, right? So rotation about the x-axis, z-axis, x-axis, or whatever your favorite Euler angle representation is. And then this sort of represents the exponential coordinates as we know from Rodrigues' formula, for instance. But essentially, if you think about rotations in the context of as a Lie group, then you're guaranteed that these two alternative ways of looking at rotations exist. And of course, we know them. We associate those representations with Euler and Rodriguez. And the same thing for SE3. Again, I can tell you the same story, but and if you look in the books that I told you, a similar story, you can plow through it, and essentially it's a 6-dimensional story. So that's as far as I want to say about manifolds. Again, the main message being, if you think about Lie groups, it's not just about group operations, it's also about differentiation. And the fact is, that's what makes Lie groups unique. The third thing I wanted to tell you about is about tangent spaces. So if you have a manifold, and here's a point P, then you can basically, in 2 dimensions, clearly you can draw tangents to a surface, and you can ask what are the vectors on that surface. So in 2 dimensions, this is easy. In 3 dimensions, it becomes hard, right? Because you don't have a way of visualizing a tangent space in 3 dimensions to a 3-dimensional surface. So remember, the surface is not a 2-dimensional surface in three dimensions. It's a 3-dimensional surface, and we don't know how to embed that. At least we have to put on a 4-dimensional glasses to sort of see a 3-dimensional surface, and we don't have those. So to think about this more abstractly is harder when you go beyond 2D manifolds. So there are 3 ways of thinking about this. So first is the way I just presented, which actually fails beyond one 2D surface in 3 dimensions at a point. But here's another way of thinking about it, which has nothing to do with the dimensionality of the space. So imagine, now we've already done coordinates, we've already done coordinate charts. So think about coordinates on a manifold, right? So these could be your exponential coordinates or product of exponential, whatever you want. And then you define coordinate curves. So what are coordinate curves? So coordinate curves are those curves that you generate by fixing all but one coordinate and varying one coordinate, right? So the x1 coordinate curve, I'm going to fix x2 and just vary x1. If it's a 3-dimensional manifold, I'm going to fix x2 and x3 and just vary x1, and I'll get this curve. Likewise, I'll get x2 if I fix x1 and x3. So you can define coordinate curves and then ask what happens when you just change one of those coordinates by an infinitesimal amount. So that will give you a tangent. Essentially, tangents can be viewed as tangents to a curve, and one way of generating curves in higher dimensions is by writing down these coordinate curves. So that's another way of visualizing it. So if you talk to differential geometers, they'll basically ask you to think about derivations, which sort of generalizes the concept of a derivative. So if you look in, this is an excerpt from the appendix of Murray, Lee, and Shastri. So it defines the set of all derivations. And just let's take a look at this. So this is basically the set of all continuous functions, infinitely differentiable, defined at a point P and its immediate neighborhood. So if I go here, imagine functions on the manifold that are smooth functions of points in this neighborhood. And imagine the set of objects that map from these functions to the reals. And insist that the derivation is actually satisfies these 2 properties that you actually see in linear algebra with vector spaces. So this is basically saying if I have one derivation and another derivation and they add in a logical way, they operate on this function that I've just picked. So I can either add the derivations and operate on a function, or I can operate on the function and then add the results. And this one is essentially saying that if you have a scalar coefficient, then you can take alpha times xp, or you do alpha times xp times f. So this is what you see for vector spaces, and it's not too hard to see that all derivations are in fact vector spaces. So physically, what does this mean? Well, these are nothing but directional derivatives. So think about f as a function and think about the problem of finding out the rate of change of f along a direction x. So imagine you're on the Earth's surface and f is temperature, and I want to walk east or north. So let's say x is east, y is north, then I can think about the rate of change of temperature as I walk east, or the rate of change of temperature as I walk north. So these are nothing but directional derivatives. So in the context of a Lie group, let's say you have a homogeneous transformation matrix. This could be the end effector of a robot arm or whatever mechanism you have. And let's say it's changing as a function of time. Right? That's your curve. Right? We get curves naturally in mechanisms, obviously. So now I want to find the velocity. Well, I differentiate the homogeneous transformation matrix. I get dA dt. Right? So that's the rate of change in the matrix as a function of time. So it has no structure to it. So remember, the homogeneous transformation matrix it's got it's a 4x4, so it has 16 elements. The bottom row will give you zeros, but you'll have the other elements, 12 other elements, which really don't have any structure. But that's what this vector is. Right? So at that point, you can think about coordinate curves. Now, I've just made this a two-dimensional manifold just for visualization. In general, it could be a six-dimensional manifold. How do you write dA dt? In order to make sense of it, you can break it down into partial a partial x1, where x1 is the first coordinate, times x1 dx1 dt, partial a partial x2, and then dx2 dt. So this is just a chain rule. So we know we can do that anytime you have a set of coordinates. So now let's piece out the x1 dot and x2 dot, call them alpha 1 and alpha 2. Think of those as speeds, because really this is the rate of change of x1, rate of change of x2. So these are joints of a 2 degree of freedom robot arm. One is, let's say, the shoulder, the other is the elbow. Well, this is simply the rate of the shoulder joint rotation. This is the rate of the elbow joint rotation. It's what's left that I'm most interested in. What is left are these partial derivatives. So partial a partial x1, partial a partial x2. So those are those directional derivatives, or the derivations. So along this one and along this direction, the two directions of interest. Right? And more generally, I have 6 coordinates, and there will be 6 terms in this expansion when I do the chain rule. Now, in order to understand what these directions are, again, the rate of change of a homogeneous transformation matrix with respect to a coordinate doesn't really lend itself to physical interpretation. But what you can do is pre-multiply it by A inverse, right? And so, for instance, you get partial A partial x1 pre-multiplied by A inverse, partial A partial x2 pre-multiplied by A inverse. And that has the structure, as you've seen in previous talks. These essentially look like twists. And so this way you can get basis twists, right? So this defines the set of all possible directional derivatives or derivations or tangent vectors you can write at this point. So this is only valid at that point because I've done A inverse, and A depends on where I am. But at an arbitrary point, if I want to find out what's the basis of all possible ways I can move, that basis can be naturally found by taking partial derivatives of A with respect to the coordinates and then pre-multiplied by A inverse. You can also post-multiply by A inverse, and we'll come to that. But this is a way of thinking about the tangent space of SE3 or SO3. So, for example, if you look at a robot manipulator, a way of thinking about the basis is by, again, looking at A inverse times partial A partial x1, x2, x3. And if you take those coordinates to be the joint angles, one for each axis, you can essentially find the basis twist. And this turns out to be nothing else than the Jacobian. Right? So essentially, these are the columns of your Jacobians if you take x1, x2, x3, etc., to be adjoint angles. Jacobians are usually messy, and the only thing I've done differently in this picture is essentially transform the Jacobian to an intermediate frame. So this intermediate frame, so remember that you have A1, A2, A3, A4, A5, A6, the 6 concatenation of the 6 homogeneous transforms. And what I've done is simply write down those basis twists in an intermediate frame which happens to be located here at the point of concurrency of 4, 5, and 6. And that gives me a very simple expression. Here, L, N, etc. are the joint offsets and the link lengths, and all of these are sines and cosines of theta 4, theta 5, and so on and so forth. Any questions before I move ahead? Tangent spaces or twists? This was my class. I wouldn't move ahead until I had at least one question. If I didn't get a question, I would start asking questions. No questions? Yes?
Could you explain again why you left multiplied the inverse matrix? Why did you left multiply A inverse?
Why did I left multiply A? So again, I want you to visualize the rotation matrix and think about the changing rotation matrix and how it would change, right? And think about the derivative of a rotation matrix. It has no structure to it, right? So R dot, you know very little about R dot. But if you take R dot and you pre-multiply it by its inverse, right? So you know that this has some structure. And why does it have some structure? Well, you know that R transpose R plus is equal to the identity. And if I differentiate this, I know R dot transpose R plus R transpose R dot is equal to the zero matrix. And from that, you basically get that this is a skew-symmetric matrix. And the components of this basically give you the angular velocity vector. Right? This is true for rotations. Something similar is also true for homogeneous transforms, and you get that by looking at this. So for instance, this guy will actually give you a 4x4 matrix whose elements essentially look like that. If I'd only looked at rotations, I'd only get 3 elements.
Okay. But in this example, you're not looking at SE3 anymore, you're looking at another space.
No, this
configuration
is SE3.
space
This
of
is SE3. So I could do the exact same thing, and I don't want to do it because it was done in the previous talk, or I can do it again for you offline. But if this thing again has some structure to it, but the minute I differentiate this, I get this, which has very little structure. But in order to recover the structure, I essentially have to do the pre-multiplication. Okay? All right, so the other, the fourth thing I want to tell you about is the relationship between Lie algebras, screw systems, and the set of all vector fields, in particular left invariant vector fields. So again, I want to go back to the product of exponentials notation that was introduced in the last talk, and ask, what is the natural basis for SE3? And I would argue that you want to think about this basis. So for instance, I told you earlier that this has no structure to it, but if you look at, if you left multiply by the homogeneous transformation matrix, you basically get 6 elements, and those 6 elements are either here, 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 there, or there. Right? So those are the 6 elements of interest. So if you look at this, the first 3 elements represent pure translations in x, y, and z, and the last 3 elements represent pure rotations about the x, y, and z axes. So if you take dA dt pre-multiplied by E inverse, you're going to get essentially the coefficients corresponding to these guys. I'm sorry, this is, I screw up here, so it should have been, it's over here, sorry. Never mind, let's I don't know what happened here, so let's just take a look at this. So this is just partial A inverse dA dt, and I'm writing this now in terms of this basis and the coefficients Ti, and that's essentially the set of components of an instrument. Now, each of these twists also define vector fields. So instead of thinking of them as a 6x1 vector, I can also ask, if I have a twist T, what happens if I start from the identity and continuously execute a motion with the same twist T? In other words, here I'm holding T constant, and I'm just changing A according to this equation, right? So the recipe is that you take the twist T and you pre-multiply by A, you advance forward. And now you have something new, you again, you post-multiply by T and then you advance forward. Again, post-multiply by T and so on and so forth. If you do that, you'll basically get a curve. And that curve will be the integral curve. And there's a vector field that's associated with it. And you really cannot separate the twist T or from the vector field and the integral curve. Okay? So if you look at the twist T, it's obtained here by taking dA dt and pre-multiplying by A inverse. Or you're getting dA dt by post-multiplying A by the twist. So these three things go hand in hand. The twist, the vector field that you get, which is dA dt, and the curve that you get. Right? Does that make sense? So what we've done is essentially gone from an infinitesimal vector t, a twist, which is just angular velocities and linear velocities, to a finite motion. So this is a finite twist, or a finite screw motion. So essentially you're saying I'm going to keep the velocities at a constant value, and I'm going to move. And that gives you essentially a finite motion or finite screw motion. So there are two ways of doing this. One is using A times T or T times A. Right? So again, T is the same in both cases. I'm going to give you a twist T, an angular velocity and a linear velocity. Yes?
Is that supposed to be A inverse T or
No, AT. So again, I don't know if you can see what I do with my black. Okay. So if you take dA dt, you have one of two ways of generating something sensible from it. One way is you pre-multiply by A inverse, and the other is you post-multiply by A inverse. So I'm going to call this multiply from the left, multiply from the right. So in this case, I'll get dA dt pre-multiplied by A inverse, and in this case, I'll get dA dt post-multiplied by A inverse. Okay? So what I've done here instead is essentially take T, define T to be A inverse times dA dt. Here, I've defined T to be dA dt post-multiplied by A inverse. So for the same T, there are two ways of generating derivatives, dA dt's. So if you do the integration and you generate the vector fields, and then the integral curves, you get two different curves. Right? And I've called these A sub L of t, A sub R of t. Right? So again, one corresponds to the post-multiplication by t, this corresponds to the pre-multiplication by t. they're two different curves, even though the twist in question is the same. So in one case, you get a vector field that's left invariant, right? In other words, if you change your origin by a map which corresponds to left multiplication, the vector field stays the same. In this case, it's called right invariant because it's invariant to right multiplication. And again, I'll show you what this means in a minute, but the main thing I wanted to convey to you is that if you're given a twist, there are two natural ways of producing vector fields and integral curves. One is this one is that one. So to intuitively see what this means, let me take a very simple example. So here's a rectangle that I'm going to move using a left invariant vector field, and I've fixed my twist. It's basically unit forward translation and a unit clockwise rotation. So these are the speeds. I got a unit speed in the front, unit speed going this way, unit angular velocity going that way. Now these are fixed to the rectangle. So this is what you might imagine if you were driving a car and you're saying, I'm going to fix the velocity on cruise control, and I'm going to fix the steering angle. So if you do that, you're going to end up with this sequence, right? But if you're given the same set of velocities, the forward velocity and the angular velocity, you could also ask what happens if you fix those in an inertial frame. So in an inertial frame, so again, same velocities, the same numbers, but I'm going to fix these in an inertial frame. So if I take a step, right, I'm moving forward, the forward direction doesn't change, even though I've rotated. So I end up in this position. So this is a different motion, right? It's a different vector field, but it's generated from the same twist vector. So this is called left invariant, this is called right invariant. So to see why left and right, those two adjectives are used, we'll talk about that later when we talk about invariance. But basically this has to do with the fact that this is invariant to pre-multiplication, and this is invariant to post-multiplication. And again, those pre-multiplication, post-multiplication have definite physical connotations that I'll explain later. Yes?
So this, we say left invariant, so are you like multiplying rotation matrices to that, or like what exactly?
So if you're doing only rotations, then yeah, there are rotation matrices. If they are homogeneous transformation matrices, then that's what you use. So remember, in everything you've done, you pick your favorite Lie group, and you take derivatives of elements in that Lie group. So the dimensionality of whatever you're taking is the same whether you consider the element or its derivative. So if it's rotations, it's 3 by 3 matrices and 3 by 3 derivatives. If it's homogeneous transforms, it's 4 by 4 matrices and 4 by 4 derivatives. Okay? So again, formally, this is how you would, if you go back and solve these differential equations, these are linear differential equations, you can get closed form expressions, and then that's what they would look like. So one of them is going from A0 with post-multiplication through this exponential. The other one is, again, going from A0, but you're pre-multiplying through this exponential. That's the only difference. So there's this well-known theorem, I'm sure somebody mentioned this, but I didn't hear it mentioned in the last two talks when I was here, which basically says for every element in SE3, other than the identity, there's a unique one-parameter subgroup to which that element belongs. So this is how you would state it in the context of Lie groups. Of course, Shaw stated it differently. But essentially what this is saying is that if I want to join the identity to A, there's a unique trajectory, and this trajectory is a one-parameter subgroup, which means elements along this satisfy the closure property, all the properties of the subgroup, and it's a one-dimensional subgroup. So that's what a screw motion is, right? So if you were not at the identity, let's say you were at another point Q and you wanted to go to B, it's the same idea. All you have to do is figure out how to, once you understand all this one-parameter subgroups that go through the identity, by pre-multiplying or post-multiplying these one-parameter subgroups, you can essentially find the one that meets your specification, that is to go from Q to B. Computationally, you might think in terms of the inertial field, inertial frame displacement, and the body fixed frame displacement. So let me draw a picture that would clarify this. If you take, in this picture, if you essentially were to take a moving frame M and a fixed frame F, and let's say this transformation is A, and if you were to change this fixed frame to F prime, right, and insist that there is this transformation Q that relates F prime to F, well, the new motion becomes Q times A. Right? So that's left translation. You could also go the other way. You could say, well, this frame M I want to change. I've done this calculation and I have A, but what if I go to this M prime? Well, then let's say you have this transformation. I'm having a bad marker day. Let's see. So if you take, this doesn't work either.
There's another one near the laptop.
Behind. Ah, thank you. So if you were to take this transformation and call it, let's say, Q prime, then here you had Q times A, but now you would be thinking of A times Q prime. So in one case you're left translating, in the other case you're right translating, or left multiplying and right multiplying. So Q could be, sorry, A could be the screw motion, but you can essentially get two variants of this, Q from the left and Q from the right. So again, from the standpoint of screw theory, if you go back and look at Bohr's book and Schall's the statement of his theorem, they talk about this motion, but actually if you talk about trajectories, you invariably talk about trajectories with reference to coordinate systems. And so you end up with two different ways of interpreting that screw motion in terms of algebraic or mathematical representations. So lastly, it's also useful to think about the instantaneous picture. So the instantaneous picture associated with any one of these, so these trajectories, so what happens locally is not on, so what happens locally is partially on the actual manifold, but you can also think about its influence at all those points, sort of the induced map that I talked about earlier. So it turns out if you look at a rigid body, and if this is the axis corresponding to the screw motion, then every point on that rigid body essentially translates along this and also rotates about this axis. So the resulting vector field you get is something called a helicoidal vector field, which means that the velocity of any point of the rigid body is tangent to a right circular helix that passes through that point. Right? And again, that right circular helix is fixed by the screw axis, so screw axis. And so the instantaneous screw axis, again, should be not confused with the finite screw motion. So you can have a general trajectory where the instantaneous screw axis keeps changing as a function of time, but in the screw motion, this instantaneous screw axis stays the same. And essentially, associated with every instantaneous screw axis is essentially the axis, or the line, the pitch, which has to do with the velocity along the axis to the angular velocity, the magnitude of the angular velocity, and essentially, and yeah, that's basically it. So this is often called the instantaneous twist about the axis. So to just summarize, in order to represent this, we use what are called Plucker line coordinates. So here's the screw axis. And so remember, that to represent a line, you essentially need 4 parameters. To represent a point, you need 3 parameters. A line you can think of as the join of 2 points, and that may need 6 parameters. But if you want to represent it in a minimal way, you only need 4 parameters. Well, a way of representing it is with 6 coordinates, but with 4 constraints. So if you take the first 3 coordinates to represent a vector along the line, and the next 3 coordinates to represent the moment of that vector about the origin, so this is rho cross v, then it's trivial to see that this and this dot product will give you 0. So you have this quadratic identity, which is LP plus NQ plus NR equal to 0, because in one case you're representing the vector along the line, and the other case you're representing the moment of that vector about O. So the reason this representation is interesting is because it also lends itself to representing pure forces and pure angular velocities. So if you think about representing a pure force, what is it that you want to capture? You want to capture the magnitude, of course. You want to capture the direction. But you also want to tell, you want to represent where it is in the physical world. If this is the line of action, a way of representing the line of action of a pure force is by capturing the magnitude and the direction and the moment that that force forms with O as the origin. So the Klucker line coordinates essentially captures very naturally what a pure force looks like. And if it's a unit force, then V essentially gets replaced by a unit vector. In general, it's the unit vector times an intensity or an amplitude. So this is one constraint. The other constraint, of course, is that if you multiply all of these by a number k, you essentially get the same line. So, and this is true for any projective coordinate representation. If I multiply this v by alpha, then rho cross v also gets multiplied by alpha. Right? So these are Klucker coordinates. So, lastly, if you want to think about screws, then you have to think about this pure force, but you also have a pitch. So this pitch essentially tells you what the moment is about this axis. So it's h times the force. So in addition to these identities, you also have, in addition to this identity, you also have to rethink how the second identity is formed because you have this additional element. So this is true, but v times rho cross v is equal to 0, but v times rho cross v plus hv is not 0 because you have this additional h times v. Okay. Any questions on that part? Yes?
Can we get again these 2 rectangles rolling?
Sorry?
Can I see the rectangles rolling? I had a question. The rectangles that were rolling on 2 ways.
You're not supposed to ask questions. Yes?
Well, so in the bottom one, what is constant?
Oh, it's v and it's the same v and same omega, except in this case I'm keeping it constant in a body fixed frame. In this case I'm keeping it constant in a wall frame.
Right, but in the second case, you know, the v, if you have an inertial frame, right? In the inertial frame, v is not the v of this point, the center of the rectangle. It's the center at the origin of the inertial frame.
Sure.
So that thing is not an inertial frame.
Sure, but I can read. So even if I take, so you're asking about the velocity in the inertial frame. I mean, which point I use. But this is just a cartoon. I just want to visualize that using the same set of vectors, there are 2 ways of generating one parameter subgroups. And these are clearly 2 different motions. And that's the only point I'm trying to make. Okay? So cotangent space and wrenches. So I don't want to spend too much time here, but anytime you have a tangent space in a problem in mechanics, you also have a cotangent space. So if you think about velocities, which are naturally tangents to a motion manifold, you have forces that are also vectors, but you can't mix forces and velocities. So the right way to think about forces is in terms of their ability to act on velocities to give you a scalar quantity, which is power. So this is usually thought of as an action. So when you think about force, velocity, there's another set of vectors which are forces, and the scalar quantity is power. Another thing you might think about, since we've talked about directional derivatives, is gradients. And those are also dual to each other. So any problem that has any kind of physical interpretation, whenever you have tangent vectors, you also have cotangent vectors. And it's dangerous to mix them because they live in different spaces. So the short summary of this, since I really want to catch up and end on a reasonable note, in terms of time, so I won't go through this, but the main point I wanted to make is just like we had the story between tangent vectors and twists, there's another story I can tell with cotangent vectors and wrenches. Again, the key thing is the scalar quantity power that links both of these through an action. And again, I'll refer you to the Murray and Sastry book that talks about gradient vectors and derivations. And a similar treatment that I did earlier with twists, you can also do with, with forces, potential fields, components, basis covectors, and the tangent spaces. So let me skip this since it's not critical. So again, as I said earlier, you could do the exact same thing as we did with twists, with wrenches. So this is your line of action. This row gives you the moment of this force about the origin. And special cases are pure forces, in which case there is no moment other than the moment that you generate from the force. A pure couple, which is just a moment without a force. So essentially what you have is just a couple about that axis, and the axis itself is ill-defined. So all of these are special cases of wrenches. And Poinsot's theorem basically says that no matter what collection of forces and moments you have, or couples you have acting on a body, you can always represent it as a pure force and a pure couple, such that both of these are parallel. And there's a unique line of action, except in some degenerate cases. So you can always do this. So the object of interest in terms of statics is really this French axis. So let me skip this and pause to see if there are any questions before I launch into my final segment. Okay. So let's talk about invariance. So the key idea in invariance, again, is you want to ask if any computation you've done is in some way influenced by a choice of reference frames. So just backing off a little bit, you've probably seen that sometimes when you pick a particular set of coordinates, like Euler angles, versus another set of coordinates, like quaternions, your answers can be different, right? So let's say you're doing an optimization problem. You want to minimize, let's say, the rates of changes of coordinates. Well, if you do it with Euler angles and with quaternions, you get different answers. Or if you do it with one set of Euler angles and another set of Euler angles, you get different answers. So that's one kind of invariance you want to be careful about. Ideally, you want your computations to be insensitive to what coordinates you pick. Another set of questions you want to be sensitive to has to do with the choice of inertial frame and body fixed frame. So if I do a magical calculation, let's say I've calculated the best way to get from here to here. One question to ask myself is, what happens if the inertial frame were changed? or what happens if the body fixed frame were changed. Right? So as I explained to you here earlier, if I did the computation in frame F and I got A of t, if I do the same computation in F prime, what should I get? I should get Q times A of t. If I get something else, then the computation is not left invariant. Right? So if I again think about the shortest distance path from here to here, and let's say I have a little algorithm on SE3 to calculate the shortest distance path. Right? If I do it in this frame, if I get A of t, then doing it in that frame should give me the result Q times A of t. If not, then something is wrong with my algorithm, and I've actually made a mistake, because it's not left invariant. Likewise, I can think about right invariance the same way, and this has to do with the changes in reference frames. So if I pick F and M and I calculate the trajectory turning out to be A of t, if I change from M to M prime, I'm going to get a different trajectory, and that trajectory better be A times Q. If it's not, then my computation is not right invariant. So those are the two key invariance principles that you want to be thinking about. So let me take a simple example. Let's say you're doing screw motions. So I'm doing screw motions from pose 1 to pose 2. So how will I do that? Well, if A1 is pose 1, A2 is pose 1, how do you calculate the screw motion? You calculate the displacement, A1 inverse times A2. You take the log map, which is the inverse of the exponential map, you get the twist. And then that's your screw motion. Right? Well, what happens if you change the inertial frame? So if I take, for instance, I'll just do one of these, and you'll see the screw motion is actually the right computation. This is the right computation. So suppose I change the inertial frame. So basically, what I've calculated here, so this is A1 and this is A2. So if I change the inertial frame, so A1, one of these works, I think. So A1 becomes Q times A1. A2 becomes Q times A2 because I've changed my inertial frame. If I go through this computation, log of A1 inverse, which is just QA1 inverse, becomes A1 inverse times Q inverse times QA2. And this is nothing but log of A1 inverse times A2, which is essentially the same thing. So you can see by changing the inertial frame, I've basically gotten the same result. So that's a quick check to make sure that this computation is the right computation. Because if I got a different screw motion just by changing the inertial frame, then obviously I made a mistake somewhere. And I'll let you do this. It's exactly the same way. It's a little more involved, but you want to check this. Here's another one where you can run into problems, and this has to do with what people call twists of freedom and twists of constraint. So if you look at this coordinate system, which is at the center of a pencil-like object pressing down, and let's say this contact is a frictionless contact, right? So the only way that this pencil can't move is in the vertical direction. That corresponds to this twist. Zero angular velocities and velocity in the z direction, in this direction. So that's a twist of constraint. So what are the twists that are allowable? Well, you can do everything else. So this is a translation, this is a rotation about the x-axis. You know, your pencil can go this way. Your rotation about the y-axis, rotation about the z-axis. These are allowed. Translation in the x direction, translation in the y direction are also allowed. Right? So superficially, you can conclude that, hey, if I know this, I can get those by just computing the linear space that's orthogonal to that. Right? So if you were to come up with these vectors by taking the orthogonal complement of this over here, that would certainly work in this case. But if I were to change this coordinate system to that and recompute this twist in that frame and the orthogonal complement of this twist in that frame, I would get an answer that's not consistent with this and not consistent with the physics. So I encourage you to look at this. In fact, there was a series of papers that made a pretty big deal about this, but actually it's pretty straightforward. It has to do with invariance properties. And we know that on V groups there are certain types of invariance that exist. These kinds of computations are not left invariant. Another one from dynamics, and this has to do with changes in body fixturing. So you know that a rigid body is wandering around, and if I want to write down the equations of motion, I would write down the Newton's equation and Euler's equations of motion. And these are usually written along principal axes in a body fixed frame. And typically we pick the center of mass as the origin. That's the convenient way to do rigid body dynamics. Well, what if I did not want to be, what if I want to do something else? What if I pick a different coordinate system? So what will happen to this? Right? Clearly these equations will be different. We know that from Newton and Euler. So changes in body fixed frame give you different equations, which means these equations are not right invariant. Well, we know that. We know that Euler said that you have to write down these equations in a coordinate system fixed to the rigid body aligned with the principal axes. But what Euler also said is that if you change the inertial frame, the equations will be the same. So if you take Newton-Euler equations of motion of this form and you change the inertial frame, they'll be the same. So those equations are left invariant. So again, useful check when you're looking at physical properties, physical laws of motion. You expect left invariance to be an important property that should be preserved. And you could also think about metrics, and it turns out, I'll just leave you with a punchline for SE3. If you look at metrics, it turns out that you can't find metrics that are both left and right invariant. You can only find a one-way invariance. So if you want to measure lengths in a systematic way on the group of rotations or the group of rotations and translations, there is no way you can measure, get a length measure that's invariant to changes in the inertial frame and invariant changes to the body fixed frame. You can do one or the other, depending on what your applications are. Okay, the last thing I wanted to do, I really have very little time to do this, since I'm determined to finish at 5:15, which was the scheduled time. But instead, instead of going through all of this, which is 20 slides or so, I'll just give you the roadmap of how to think about a variety of screw systems. One key idea is this notion of reciprocity. So two screws are reciprocal if you take a wrench associated with one of the screws and a twist associated with the other screw, and the wrench does no work about the twist. So that's the fundamental idea, and it has to do with power. So here's the force and the moment coming from the wrench. Here's the angular velocity and linear velocity coming from the twist. And it's basically a question of doing the mechanics of computing the power and asking, is that power zero or non-zero? So reciprocal wrenches are great if you think about when you pick up a suitcase, for instance, and you're holding a suitcase, you're essentially applying zero torques, right? You just hold the suitcase in place with an extended arm. And the reason, of course, is because the wrench applied by the suitcase is reciprocal to the twists associated with the joints, and you get great mechanical advantage because of that. Right? So reciprocity is a useful concept. The natural way to do reciprocal products is by writing down the Plugger coordinates for the twist and the wrench, and basically do essentially what looks like an inner product, but essentially this L1, M1, N1 multiplies with that, and this multiplies with that, and you're adding this up. So you're kind of doing an inner product, but you're flipping things as you're doing the inner product, right? So that's called the reciprocal product. That's why it's not called the inner product. The key thing is that this notion of a reciprocal product has nothing to do with wrenches and twists. It's a geometric property. So if you take S1 and S2 and you ask when are these two reciprocal and you do the calculations, well, the best way to do it is actually to think about a wrench about one and a twist about the other, but actually it has to do with this geometrical property. So this says that if you take the pitch of one of these, which is H1, the pitch of the other one, which is H2, and if you look at the angle between them and the distance between the two axes, which is V, if this equation is satisfied, then a wrench about one of these cannot do work about the twist about the other one, or the other way around. A wrench about this cannot do work about the twist of the other. So this is, again, a useful concept, and I'll just give you a couple of, I'll skip this derivation and give you some examples instead. So for instance, if you take a single joint and you applying a wrench to it, the question is, when is this wrench reciprocal to this twist? So remember, this is undergoing a twist about this axis. Well, if this were a pure force, and if it were to intersect that, there is no way you can actually do work with this pure force about this twist. So in that setting, essentially H1 and H2 are both 0. This is a pure rotation. This is a pure force. And the value D is 0, and you can see that this equation is satisfied. In fact, if this force were parallel to this pure rotation, you would do no work. So these are useful things to recognize in terms of reciprocity. The exact same picture emerges if you replace this rotation, which is a zero-pitch twist, by a zero-pitch wrench. So this is a zero-pitch wrench, frictionless contact. So now I've interchanged the roles of S1 and S2. S2 was a wrench here, S1 was a twist here. Now S1 is a wrench and S2 is a twist, but the geometry is the same, and the same condition applies. So let me, instead of going through all of this, get to the punchline. Anytime you have contacts or kinematic constraints because of joints, there are basically two screw systems or two vector spaces that naturally emerge. So one is a set of all available twists. So think about your arm, let's say a 2 degree of freedom arm. You have basically at an instant, you have two sets of twists that you can execute. There are lots of twists that are not available, right? But the available twists are two-dimensional in this case. Well, if the available twists are two-dimensional, then you're essentially guaranteed a set of wrenches which is four-dimensional. Right? You can't argue about things that you don't have in terms of twists. So you can't say that I have these two twists, I'm going to classify, I'm going to categorize all the twists I don't have. That turns out that that doesn't make a lot of sense. But what does make a lot of sense is to say, what are the wrenches that are reciprocal to this? In other words, what are the wrenches that can be exerted on my arm, and I don't have to apply any force or actuate a torque in order to resist that? That makes sense. So that's where reciprocity comes in. So if you want to do instantaneous analysis of a mechanism or robot or what have you, you think in terms of available twists and in terms of constrained wrenches that do no work. Likewise, if you have contacts between two rigid bodies, you know what the constrained wrenches are. It's frictionless contact or frictional contact. These are easy to define. And once you define this, you immediately know what motions are allowed. And this is true even of a very complex mechanism. Imagine a humanoid holding on to something. You can do the calculation and come up with this. You'll also be able to come up with that. And the other way around. If this is easier, you'll be able to come up with that. So these are easy ways of doing instantaneous analysis of very complex mechanisms. And I'll let you run through this, but there's a whole bunch of examples on the slides. And I'm happy to take questions about any one of these. And this is really the last thing I wanted to talk about. If you look at Hunt's book, there's a classification of all possible screw systems that anyone could be possibly interested in. And a subset of the screw systems are listed here. Right? So this subset of the screw systems consists of, for example, little SO3, the V algebra associated with the rotations, the translations and rotations associated with SE2 in the plane. So again, just angular velocity about the vertical axis and the translation in the plane. This is the rotations about one axis. This set of screw systems are also Lie subalgebras, which means if you were to look at the commutation, the bracket operation in the Lie algebra space in any one of these, the result will also be in that subspace. In Hunt's book, these are the screw systems that he singles out because those screw systems also allow you to design for finite motion. And the idea again is very simple. If you have a Lie bracket operation, and after the Lie bracket operation you stay in that space, then there's finite motion that's possible. And if there's finite motion that's possible, then you can also think about it in terms of the context of mechanism design. So these subalgebras are in one-to-one correspondence with the subgroups that I showed you and with the rouleau pairs that was mentioned earlier. And these are also listed and described in some detail in Hunt's book. And as he says, they guarantee full cycle mobility. And what he means by this is it's not instantaneous mobility, it's over a finite interval. Okay, I think that's basically what I wanted to talk about. Again, these are all examples. Conceptually, it's basically the same thing. This picture, by the way, is a picture of the general two system that you can get. So if you take linear combinations of two screws, right, you get a one parameter set of screws. If you identify those axes, this is the geometric pattern that's formed, and it's called a cylindroid. So my icon in my slide is a cylindroid. So to me, this sort of typifies this thinking about mathematics of mechanisms and then thinking about the geometric underlying structure. Plus, it's one word. If you type it in Wikipedia, you'll get the wrong answer. So if you know what a cylindroid is, you're already in this strata of people that knows more than Wikipedia knows. Okay. Lastly, I wanted to do a plug for the Journal of Mechanisms in Robotics. Mike McCarthy was the editor of this, founding editor of this journal. For the last 5 years, I took it over in July. We want you to think about your best papers and submit it to this journal. As you can see, we have a distinguished editorial board. Many of the people are actually in this room. And I just want to leave you with this. And I'd love to ask questions with this in the background, so this becomes emblazoned in your memory. Thank you. I said I would finish by 5:15, 8 minutes late. Sorry. Questions?
We've got like 7 minutes for questions, so please fill the time.
No, we have -8 minutes for questions.
No, we have a little bit of, that was before questions. So you use your time wisely.
Okay. I think everybody's questioned now.
Right, so like I said before, if you have not taken the survey yet, you have 7 minutes to take that survey.